Good evening. I'm glad that you are here. Let's get started with this 11th hour review before the final exam. It was a last minute arrangement, and this was only possible because one of former students who took this class before, Kai Ming Tan, Kai come forward here, was able to help with the chat room, and so that we are going to be able to conduct this e-review to you over the online participation. Kai, thanks for doing this.
You're very
You
welcome.
took this class before. You have been in the same situation before, right?
Exactly.
All
Good
right.
evening, everybody.
Thank you very much. So let's get started then. So what I'm going to do is that I'm going to present the summary of the lectures that we have done since the midterm 2. We go from there with all these details, and that is not going to be a very comprehensive review. You have to do that by yourself, okay? So what I'm going to do is just briefly touch base on the major points that we have discussed in all this lecture so far. So let's get started here. That was lecture 14, where we studied the role of hydrogen bonds in to the secondary structure. So we discussed this thing in class. We talk about the secondary structure, and we talk about the Ramachandran's plot and how it shows that although there is possible rotation for these bonds, there are preferred position or preferred angles where this bond exists. So let me highlight in here with the laser point in here. So there are the two types of structure, the beta strand and the alpha helix, which are the major structures. So what this plot tells us is that although the possibilities are enormous, there is a certain group of positions that these angles exist in proteins, and therefore there are basically two types of secondary structures, the alpha helix and the beta strand. So that's the issue about this plot here that shows that two main regions that are allowed. We talk about the alpha helix. We discuss a few things about the alpha helix, which are very important. And let me go over this issue here very briefly. We talk about the one turn of the alpha helix going from one top to the other one. It takes 3.6 amino acid residues. And this was the major discovery of Linus Pauling, and he got the Nobel Prize for that. So we also look at that there are 13 atoms in between the hydrogen donor and the hydrogen acceptor, which are here highlighted in the cyano, the light blue color, the 13 amino acid residues that come from this hydrogen bond to make the donor and the acceptor. So therefore, these alpha helix are also known as 3.6 13 helix because they have one turn, 3.6 amino acid residues, and there are 13 atoms between the donor and the acceptor of the hydrogen bond in the backbone of this helix. So we look at this helix and we look at the hydrogen bonds when we see one group here that represented by this C double bond O, that would be the carbonyl, and the face of that carbonyl, there is an NH at the other end. So therefore, we have hydrogen bond formation within the helix. Many people believe that this is the foundation for the stability of this helix. But one has to keep in mind also that these hydrogen bonds are going to form anyway, either within the helix or with the water from the outside. However, this is a very important point that this formation of this helix make a number of hydrogen bonds within the structure, in this case here, of the alpha helix. We talk about also that because this has a dipole, the dipole is always negative in the C terminus and the positive in the N terminus. So we also mentioned that some of the amino acid residues in the N terminus and some amino acid residues in the C terminus do not make a pair with the hydrogen bond because there is not another, there is a donor, but there is not an acceptor, or there is an acceptor, but there is no donor. So those are make up hydrogen bonds with something else include water or other amino acid residues that are going to be at the end, at the termini of the helix. So the helix always started from the N terminus and it goes to the C terminus. That's the way that we look at proteins and everything related to the structure of proteins. Another type of structure that we talked about was the beta strand. The beta strand, they have two types, the anti-parallel and the parallel beta strand. And we talk about the hydrogen bond formation here being different side by side. So there's a red here highlight the hydrogen bonds that we see in the anti-parallel, and anti-parallel gets a very nice position of the hydrogen bond, just straight there. For the case of the other ones, let me get rid of this thing here. Sometimes they send the signal here that gets on the way. So let me get hit. Okay, so get rid of that and then go back to the laser point to show here that this conformation between the extension from one amino acid extends for 3.5 angstrom as opposed to the helix that's 1.5. And if you have 3.6, we have 5.4 for one pitch, right? Here we have one amino acid advanced 3.5. Therefore, it's called the extended conformation. And this is the same thing, but this is all in parallel. The beta strands are in parallel, and they do not match as nicely as they do when they have the anti-parallel configuration. So there's a little bit shorter here, 3.2, and the angles, we don't need to remember those angles. These are not important question, important issues. The very low yield is probably never going to be any exam, either here or somewhere else. Any exam in biochemistry is not going to ask these numbers anyway. So it's important to know what's the length of this thing, where the hydrogen bonds are, and the things of that nature. We talk about examples of proteins that have this configuration, the local configuration that we call, with the alpha helix and the beta strand. And this is one example that we talk a lot in classes, the silkworm pheromone binding protein. We show a very helical rich protein with 6 helix and sometimes 7 helix, depending on the pH of the solution. So that's basically alpha helical type of proteins. And we talk about also some other proteins. Again, this is a situation where this protein exists in two conformations, the lower pH and a higher pH, and they have a little slightly, not slightly, but the dramatic conformational change going from one to the other, and the one formation of one of the helix, right, that we discussed in class, and we've brought that model that one student from this class gave to me as a present, which was a very nice thing because it shows very clearly, even if you don't see the slides, but when you look at that, you see the conformational change. Let me talk about that very briefly again. So this is the change. This is the center here where we have the pheromone. In this case here, this pheromone is called bombicol, but pheromone is like a hydrophobic chain with a polar head, like a carboxylic alcohol or something polar. In this case here is an alcohol. It looks like a fatty acid, okay? So resemble fatty acid that has this long hydrophobic chain and a little bit polar head. That's the same case here of this pheromone. So this pheromone is carried by these proteins inside of the binding pocket is right, so that's encapsulated the pheromone inside. There are various amino acid residues that stay in the surface, has charge, and therefore it becomes like a molecule, a complex of a pheromone and a pheromone binding protein now that's soluble in water. The pheromone per se was not soluble in water, but combined to the pheromone binding protein becomes a complex which is soluble in water. But the point that I want to make here is not that. The point is that I want to make is that this C terminus of this protein, when bound to the pheromone, is unordered. And when it binds to the pheromone, becomes a helix here. That's what we call the 7th helix, the alpha 7, that becomes here and it gets inside of the binding pocket. So this helix has a high affinity to the binding pocket than the pheromone. So it's a competition here. Whoever that has a high affinity is going to be bind to that binding pocket. So that's how this protein works, but it's more like an example of alpha helix in here. And we have also some beta strand. This is a beautiful protein with all this beta strand there. You see parallel and the anti-parallel beta strand in this case of this protein, which is a channel. It's called the porine. We have lots of pores in the cells. And in the last day of class, we talk about aquaporine. That's a particular pore that's only for the passage of water, right? But there are many other pores in the cell, and they are all proteins. We also talk about some of them that have a mixture. This was a nice one because it's almost like half of the protein is alpha helical and the left of the protein is beta strand. So it's a protein that's almost 50-50. Then we went on and talk about this cooperative and non-cooperative binding. And we discussed this curve in class a great deal. We show these two types of a curve that one can get when you study the binding of a ligand to a protein. In one case, we see the steep increase in here and the plateau there, which give a quadratic hyperbolic. And we see another one, another type that's increases slowly and then start increasing very rapidly. Indicate that in the beginning, it was very difficult to bind, but something happens that facilitates this bind, and now the curves go very high, like the other curve that we see before, the one in black. Okay, so this is called the sigmoid type of curve, because if you look in here, it's almost like forming an S shape. That's why in biochemistry we call it the sigmoid curve. So the sigmoid curve is an indication of a cooperative bind, is a positive cooperativism, and we discuss a great deal about the positive cooperativism when we study hemoglobin. So when we look at this curve, if you get the 50% of the bind, this represents the bind sites that are occupied. We can give you this scale here from 0 to 1 or 0 to 100. If you go at the 50%, when 50% of the bind, the pockets are bound, that's the concentration that leads to that 50% is called the KD, the dissociation constant. And that's a reading for the affinity of the protein for that particular ligand. So KD, the higher KD means low affinity, and the lower KD means high affinity. For example, in these two curves in here, it's very clear that the black one has a very high affinity because the KD is so small that it's even difficult to trace that in this particular display. We would need a little bit more extended curve to be able to see the KD there. And with the green one, you see that the KD is to the right. So that has a low affinity, higher KD, low affinity. We discuss in great detail about this hemoglobin, and we start with myoglobin. We studied this bind, and we discussed this very nice structure here of the heme group that has a very nice place that fits nicely. So they have a very high affinity, and they get stuck in the protein. And then becomes part of the protein, a prosthetic group, right? The protein by C by itself, it was not able to do the whole job, so it recruited something else. In this case, it's a heme group. And we discussed this heme group, and we mentioned that this has an iron bound to the 4-nitrogen. Remember, this 4-nitrogen here has nothing to do with histidine. These 4-nitrogen here are nitrogen from the heme group, right? They are connected with what we call the coordinate covalent bonds. So there are 4 coordinate covalent bonds in here, right? So we have 1 nitrogen donate the pair of electrons that are going to be shared covalently by these 2 species, by the nitrogen and by the iron. So that's given by 1 and shared by both. So it's not an ionic bond. It's not a regular covalent bond where each one participates with 1 electron, but rather 1 gives the pair of electron, and now it's our business is a 50-50 now. So that's one type of covalent bond, is coordinate covalent bond. And we have 4 of them bound to the nitrogen of the heme group. And then one of them, the iron can make 6 coordinate covalent bond. Iron 2, which is very important. Another one that make a covalent coordinate covalent bond is make that bond with the histidine. So the so-called the proximal histidine, the histidine that's linked covalently, and we know the whole thing about the conformational change, cooperativism. It all is the foundation of all this thing is that link that make this thing move around when it binds to oxygen. So as we look here inside, we are going to see in this particular picture, we are going to see here the proximal histidine that's linked, and the icon for the proximal histidine is to see that there is a bond associated with the iron. There's a coordinate covalent bond. Now, this heme group here, this iron, this heme group is having 5 coordinate covalent bonds. 4 to the nitrogens of the heme group around, and 1 to the proximal histidine. And there is one space now for oxygen or for some other ligand to bind there covalently to that particular oxygen. And on the other side, there is a distal histidine, which is not shown in this picture here. But there's a distal histidine that sometimes get on the way of the bind of some other species, for example, make it difficult for CO or carbon monoxide to bind, but even so carbon monoxide ends up binding to that unit. What's important is to remember that the distal histidine is not coordinated covalent bound to the heme group, not at all. It helps stabilize the oxygen by making hydrogen bonds with the oxygen once bound to the heme group. So we discussed this thing in length, so that's the highlight here. And because this histidine appears always in the number 8 amino acid residue of that F helix, whether it is myoglobin or hemoglobin from humans, from fetus, from adult, from fetus, or from other animal, always in the position 8 there is histidine. So this is so well conserved that is so named F8. Always we refer to that by F8 because it's always in the same position. And that histidine F8, like we said, is linked to this iron. So now when oxygen comes from the other end and binds to it, it's going to move this thing around, okay? Because this structure is not flat as it's shown in here, but it rather make a dome. So now when it binds, it changes a little bit this position of this iron. And that's the moving of that iron that's caused this entire change in the conformation of the protein. Change, and the tertiary conformation of the protein change. And remember, change of one unit, like for example, let's say the beta unit or the alpha unit is changed, and the other units that are a part of the quaternary structure start change as well. So that's a very important issue in terms of cooperativism, is how this little change in the position of that iron is going to affect the entire structure of the protein, and it causes so much better binding afterwards. So here it is. In this case, we have here 2 histidines depicted in here, and we have to be cognizant of the fact that sometimes this histidine comes on the top, sometimes on the bottom. It doesn't matter on the right side, the left side. All we have to look is that which one has a dot there, which one is directly connected to the iron. So that's what is going to characterize which one is the proximal and which one is the distal histidine, right? So in this picture here, we have, this was from a protein bound to oxygen, and I removed the whole structure and I let only that heme group and some of the residues around so that we can see better. So what we see here is that the iron and is connected to the proximal histidine here, this time on the bottom. We see now the distal histidine distant from the bind pocket, and we see now the molecule here of oxygen that's bound to that. So there are hydrogen bonds in here. That's what makes this stabilize Because once we have a bound of oxygen, if something else make a hydrogen bond, further stabilize that bindings, okay? So that's what makes a little bit stronger the composition of the bound molecule after all. We talk about hemoglobin, compare hemoglobin with myoglobin, and we know that the myoglobin is a monomer. So all these things that we're talking about change a little bit the tertiary structure of myoglobin. But what's important is not the change in the tertiary structure of myoglobin. What's important is the consequence of that for the entire structure, the quaternary structure of the protein, like it happens in hemoglobin. Hemoglobin depicted here on the right side is a pair of dimers. That is the alpha 1, beta 1, alpha 2, beta 2, and they make a bond, and they make a tetramer, a dimer of dimer. And we know that this alpha is a little bit short, by 5 amino acid residue short, so they don't have the D helix, and the beta is 146 amino acid residues, a little bit longer. So this is important to keep in mind. And then we relate all this thing with the physiology, okay, of oxygen transportation. Is a very important issue, and we're going to have that not only now, but later on we're going to have the same issue, especially those students that are going to in the trajectory for in a pre-med now, in a project for medical school or some medical profession. At some point, this is going to be part of your life. So what we see here is the curve with the binding curve of saturation of oxygen here. And this is the partial pressure of oxygen that we talk about, partial pressure in the lung being high and the partial pressure of oxygen in the peripheral tissue being low. And we see here that's a very big gap between the periphery and the lung. So in the lung, these proteins can get a huge amount of oxygen, but when this protein comes to the periphery, gets a much lower amount of oxygen. So this is the amount of oxygen that this protein depicted here is going to be able to deliver when it comes to this point of very low. In this case here, I exaggerate a little bit to make the point very clear. I went as low as 10 torr, which is a very low pressure. Typically, we're talking about 40 or 35 or 20 torrs in the muscles during very high activity. But in order to make the point very clear, I went way down so that we see that there is a huge amount of oxygen that is going to be dropped for this protein when this protein comes from a situation like in the lung to a situation in the peripheral tissue. We talk about this process being an equilibrium, and there are three different ways of look at this equilibrium. One way is talk about the ox-deox form of hemoglobin, the deox form being the form that's not bound to oxygen, and the ox form that's bound to oxygen. We also talk about the tense form and the relaxed form. The tense form doesn't want to bind oxygen, and the relaxed form is the one that wants to bind oxygen, right? So when it comes to the lung, it becomes in the relaxed form, and this thing is carried to the periphery. At the periphery, it changed. The equilibrium shifted towards the tense conformation that doesn't want to bind. So that's the deox form of hemoglobin. We look at that as an equilibrium also, and when hemoglobin binds to oxygen, generating HbO2. Sometimes we wrote the HbO8 to emphasize that there are 4 molecules of oxygen bound at most and generate protons. What's important here is that these generate protons, and the protons are important because carbon dioxide reacts with water produced by carbonate and H+. So the two things are related. Once you have production of carbon dioxide and the carbon dioxide reacts with water formed by carbonate, is going to generate protons, and if you generate protons, you are going to affect this equilibrium here. So if you generate protons, you are going to affect this equilibrium. It's going to be shifted to the left, right? So that's going to be, if you have higher concentration of protons, equilibrium go to the left, the unbound form of this beautiful protein named hemoglobin. Here's again the same curve that we studied before, And we studied another thing that's called the Bohr effect. The Bohr effect, known before we knew anything about this structure protein. Bohr find out that when you lower the pH, this is going to change, and the curve is going to be shift to the right side. So that's a very important observation, historical one. If you lower the pH, we shift this curve to the right. Now we know why is that happened, but at those days, it was only an experiment, an observation, without know the mechanism as yet. So it's called the Bohr effect. The affinity is inversely related to the acidity, high acidity, low affinity of the protein. Okay, so in the lungs, this hemoglobin is going to, the histidine of this hemoglobin is going to be deprotonated, because in the lungs the pH is higher, and in the periphery the pH is lower. So when the pH is higher, it's going to be deprotonated, because when they deprotonate, histidine becomes uncharged, and now is not going to be able to make the salt bridge with the negatively charged amino acid residues that are there, glutamate and aspartate. And things reverse when they come to the periphery, right? Because the periphery is rich in protons. Where these protons come from CO2 that's reactive to water and releasing protons. These protons are going to be bounded to this histidine and going to protonate this histidine. Now the salt bridges are going to be formed. This structure become a little bit more dense than the other structure before. So all these things going on at the same time as the protein are flown through the peripheral tissues and getting back to the lungs. We talk about the BPG, a very important effector. BPG is one of those that is very important to lower the affinity of hemoglobin. Hemoglobin is beautiful because it has high affinity when it's very high concentration, low affinity when it's lower concentration of oxygen, which is a very important feature, because we don't want a protein that has a very high affinity of oxygen, but it would hold that oxygen forever. We want capture and release. Capture and release, that's what this protein has to be doing. And it does that in great part because of BPG. BPG, there's a bind pocket for BPG in the protein, a very nice place there that the protein can get into that. And by binding to that, it causes that the protein is not going to be able to bind as much oxygen. So the affinity change, so that decreases the affinity for oxygen. So BPG makes hydrogen bonds and salt bridge. Do you need to know which number, which amino acid residue? No, we need to have a good idea what's that kind of thing, but it's very low yield to memorize these numbers of these amino acid residues. I'm not talking about my exam in 2 days, but I'm talking in general terms that we don't need to memorize all these numbers, because this is not what's very important. The concept is what's important. Okay, so this is a molecule that has negative charge. So obviously positively charged amino acid residues are the ones that are going to stabilize or make salt bridge with these molecules. So we highlight in class this lysine 82, histidine 143, and the histidine 2 in the endoterms, and then in terms of the subunit that make this cross-link. Do you need to remember that? I would not recommend that. Okay, so without BPG, the hemoglobin has a higher affinity for oxygen at low pressure. And this is not a good thing, because if you have the higher the affinity at low pressure, the more oxygen the hemoglobin is going to be holding, and they take it back to the lung. And the lung doesn't need oxygen. There's a lot of oxygen available to the, for the lung. What the lung wants to do is to deliver, to drop this oxygen to the periphery, right? We show, this was a side story. I didn't even share this slide with you, but I showed this slide in class to show that the PPG has a significantly higher affinity for the hemoglobin in the T state, because there is this hole here that's going to be changed dramatically when the protein changes to the R state. When the protein gets to the R state, there is no space for BPG. So BPG has no affinity to hemoglobin when it's in the R state. In the T state, when the conformation is there, that's the right place for BPG to get in. And then because of this high affinity of BPG, that makes the protein drop oxygen when it comes to low. What's the effect? Which one happened first? That's not important here. The important concept is that because of PPG binds to this protein, it's going to cause the protein to release oxygen. Hydrogen H plus bind to this protein is also going to cause the drop of oxygen. But which one is important? Which one coming first? That's not the issue. The issue is that we understand the species and we know that this whole thing is going on at the same time. We talk about the fetus, that fetus having a different situation because the fetus is not going to get outside and breathe the air that's available to us, but rather is going to be entirely dependent on the mother. So the mother is going to deliver not the only nutrients and everything through the placenta, but also oxygen. So oxygen is transferred. So what happens is that the fetus has a different type of hemoglobin that allows the oxygen that's dropped for the mother, because when it comes to lower percent of oxygen, some of the oxygen cannot be accommodated by this hemoglobin. Hemoglobin is going to drop some of this oxygen, and what happens is that the fetus has a different type of hemoglobin that still can hold that much of oxygen. So we showed in class this diagram here with the hemoglobin for the fetus to be shifted to the left. When you shift to the left, what we're going to do is that we're going to increase the affinity for oxygen. Well, in general, this would not be a good thing to increase the affinity of oxygen because we lose drop in oxygen. But in the case here, that's a transfer from the mother to the fetus. That's a very important thing. If the fetus and the mother would have exactly the same type of hemoglobin, then the mother would drop, but the fetus could not hold that anyway. So they would undergo hypoxia, right? They would undergo lackage of oxygen and ultimately die. But this was the structure of hemoglobin from for the fetus is different. Has, instead of this beta, has what we call the gamma chain. So that's a different structure. The fetus also has less BPG and also much lower affinity for BPG. One can even think in a simplified way, there's no binding at all of BPG. That's even possible to go around and think to make the problem much clearer in your mind. So the fetus has shifted to the left as compared to the hemoglobin of adults. We summarize in class all what's going on with the shift of this curve, which is very important because either here, I mean, 2 days from now, or some other class, or maybe if you're going to take MCAT or things like that, it's important that you keep that thing in mind. What happens when you shift this curve to the right? What are the factors that make this shift to the right? One is lower pH, which we already know because this is the Bohr effect. It's very easy to memorize. Bohr effect is a shift to the right by lowering the pH, right? And everything else is by increasing, BPG increases, CO2 increases, temperature increases. And of course, if you're going to look at a shift to the left, it's going to be everything that's going to be decreasing, right? Except for pH, that's going to be increasing. So what we have here, if you wanted to have a shift to the left, then we just have to have the reverse of this. This is increasing. If you decrease one of these three factors here, BPG, CO2, or temperature, the shift is going to be to the left. pH, as we increase in here, then we are going to shift to the right. But if you decrease the pH, if you increase the pH, then we're going to shift to the left. Right. One thing about pH that we have to be always keep in mind is that sometimes this question comes in the form of a concentration of protons. Instead of say lower the pH, we'll say increasing acidity. It's the same thing, as you know, but we have to be thinking and pausing so that we don't get trapped in this particular situation. Okay, so that's a left shift in here, like I said, with all these factors. We also talk about this beautiful hemoglobin doing multitasking, right? At the same time that is carrying oxygen to the tissues, is also capture carbon dioxide and protons and remove this thing and carry back to the lung, right? So we discussed two diagrams. I'm going to go over very quickly on one of them, and you please review the other one later. So we have CO2 coming from the outsides that's been produced by the tissues, by the activity of the tissue generates CO2. CO2 gets in the plasma. This represents the liquid solution around the cell that we call the plasma, right? And then gets inside of the cells that in case of the blood cell, we call that the erythrocytes. And the erythrocytes then are going to have enzymes in here, like carbon anhydrase, that's going to speed up this reaction of the formation of carbonic acid, H2CO3, which is immediately dissociating bicarbonate. So in other words, you are pick up CO2 and make bicarbonate and generate protons. That's very important to keep that in mind. You are generate protons. We don't want to increase the concentration of protons in the tissue very high, because one thing that the body always try in terms of homeostasis is try to balance the pH. We don't want anything that causes an increase of protons, because it becomes an acidic environment, and that's not healthy for the living of the cell. So on the other hand, this CO2 also binds covalently to the inner terminals of hemoglobin, and it forms a bond, there's a carbonate there, and that thing also generates a proton. So we have CO2 coming in, we have CO2 now that's going to be binded to the protein, but it's going to generate protons. We're going to have CO2 that's going to generate bicarbonate, but also generate protons. So where these protons go? These protons are going to be buffered by this hemoglobin, because hemoglobin binds to those protons and carry those protons that are going to be released later there in the lung. So these protons coming here, just one information here. Okay. So I'm going to speak a little bit slower because it looks like the audio is not catching with my pitch. All right, thanks very much, Kai. So let me slow down here because it looks like the audio is not coming in the right rate out there. Anyhow, so we are saying that the carbon dioxide is going to be generating here, form a bicarbonate, and they generate protons, and also CO2 is going to bind to the terms of the protein, generate protons. The protein binds to these protons, and as binded to the protons, the equilibrium of hemoglobin that came here bound to oxygen, and now is bind to these protons, and these protons are going to shift the equilibrium so that the protein is going to be liberated oxygen. So at the same time that they are getting CO2, they are also deliver carbon dioxide. And there, of course, here also, this BPG is bind to the protein, right? Binding to the protein. But the point of this cartoon here, it was to show that there are three routes for the carbon dioxide to be released from the tissue and to go out to the environment. One is circulating as bicarbonate in the plasma, which is very important for the maintain the buffer condition of this blood. Another one is by bounded to the hemoglobin. And of course, a little bit of carbon dioxide can bubble into water and it become a solution of carbon dioxide. So the blood is no exception. The blood has also carbon dioxide, dissolving it, carbon dioxide in the form of bicarbonate, and the carbon dioxide in the form of bound to hemoglobin. So these three avenues that carbon dioxide is going to be carried outside of the peripheral tissue. We talk about oxygen. You please review that. That's also very important. Then one of the last topics in class was the enzyme kinetics. And we discussed this, how these enzymes are change the pathway of the reaction in a way that the reaction, although remains the same energetics of the reaction, the same delta G at the end, but the delta G of activation becomes much lower. Of course, I made a simplification here of one single step. There are reactions that are multiple steps. But what matters is that what's the largest delta G, that the step that determines the uh, uh, speed of the reaction. So that's the one that we wanted to lower the maximum we can, right? So that's the step that the highest one, we wanted to decrease that. As you decrease that, the reaction becomes faster. That's exactly what the enzyme does. And how they do that, we pick up the example of carbonic anhydrase, which is the enzyme that we just talked about in the context of hemoglobin. And here we are talking about carbon anhydrase in the context of an enzyme itself. What is it doing there? It's bound to water, and it causes that this reaction goes to a different route. Now, if this reaction would have no enzyme, oxygen has to bind, to hit directly molecules of oxygen and carbon dioxide to be able to react, right? Because we need interaction between molecules to be able to react. What this enzyme does is that they pick up the water in the active site of the enzyme and makes the water dissociate more. So the water becomes more acidic when it's bound to this enzyme. So by dissociate more, we generate an entity now that's hydroxide bound to the binder site of the enzyme. Now, all we need is that enzyme to bind to CO2. See that now there's not the water in the CO2 anymore. It's an enzyme in CO2. So that would generate an attack in the carbon here and a shift of these electrons and things like that, and then generates the bicarbonate that we see here. And the enzyme is entirely recovered and it goes back to do the same thing over and over. So the point that I want to make with that example was that one route before it was oxygen and carbon dioxide directly. Another route now, carbon dioxide hits an enzyme binder site which holds a hydroxide group ready to insert in that molecule. So therefore, this different route with the enzyme's participation decreased the delta G so dramatically that the reaction that was already fast becomes one of the fastest reactions because of that enzyme. And it's very important. People that do not have this enzyme, have defect of this enzyme, they have conditions, and some of them, the bone becomes like a stone, and there are some other diseases that we don't have to go over those things right now. And then we study the kinetics, and we look at the Michaelis-Menten equation. That's the equation that we have to memorize for Wednesday. One of them, V equal V max times S divided by S plus Km. So we look at this curve here, and we examine this thing, and we call that the V max is a larger number that sometimes is difficult to measure in a curve like that. To be accurate would be very difficult because we need to have a very high concentration of the substrate. So, and in the beginning of the reaction, or in the beginning, rather say the beginning of this graph here, it represents reaction that have a concentration of the substrate very small, much smaller than the Km. As we see here, this is the Km, and if you see a concentration like that here, it's obviously much smaller than concentration of the Km. So those very small concentration generates a reaction that's a first order reaction because the Km is so small. Now that we know the Michaelis-Menten equation, it's very simple because we can just go look at that and say, well, if S is so small, this is becoming V max over Km times S, which is a very first order reaction. Okay. But before that, we analyze this thing by the concept rather than the Michaelis-Menten equation, which came later. So this would be a first order reaction. And what we have to remember here is that when you simplify this thing, we get V max over Km, and the V max over Km is then the rate, because the reaction is V equal Ks, K meaning the rate of the reaction. So that rate constant can, for the first order, can be determined by knowing the V max and the Km of the reaction. So that's something important to solve the problems. Another important issue is that for this first order reaction, we talk about the decay that exponential and the increase of the product that exponential. Therefore, we follow this formula that is S equal S0 times E to the power of minus KT. K means the rate constant of the first order reaction, and the T means the time or whatever unit of time that the K is given. If the K is given as second minus 1, then the time is going to be in second. If K is given to minutes minus 1, a power of negative 1, that means that the time has to be also in minutes. So we have to synchronize so that we have the same unit there. One way, when we need to know how much time until we get 50% of S0, we start with S, and what the time that we get 50% of S0 is called also the half time of the reaction. That we could simplify, and we already did a calculation, so we don't need to show this thing. We just plug in the formula T half equal 0.693 divided by K. Once we know K, you get the half time of the reaction without having to demonstrate that. All right, so we also show that these curves are difficult to analyze and to get the parameters from there. So sometimes we transform this graphs and get the double reciprocal plot. Instead of having V here, we have 1 over V, and we have, instead of having S, we have 1 over S. So we then get the so-called Line-Weaver-Burk plots. And we get a plot like that. Where do we go in this plot to find out the information that we need? We focus our eyes in here, and we go to the 1 over V max and 1 minus 1 over Km. So we focus on this, and immediately we can get the value that we need. You just need to find out what's the unit so that we don't get it wrong, and what's the unit of the concentration so that when you get the Km, you get it in the exact same concentration. Km can be in various types of units, can be molar, micromolar, millimolar, nanomolar, and you go from there, okay? We talk about the turnover numbers. The numbers of substrate molecules convert to products per unit of time by an enzyme under saturated conditions. By definition, Kcat is Vmax over ET. T means the total concentration of the enzyme that are bound or not bound. Enzyme unbound, we talk about that as ES, enzyme substrate, right? So we have here, just working out of this formula, we analyze that Vmax is called Kcat times ET, and then we bring the Michaelis-Menten equation. Michaelis-Menten equation called for Vmax. We already know what's Vmax in here. We plug in these numbers, we replace that in the equation. We got this, and under physiological conditions, when the concentration of S is much smaller than Km, so S is going to be irrelevant here in the denominator. And this is a very important thing, because if you have a sum of numbers in the denominator, it's not an easy calculation to do, but it is easier if the S is so small that can be neglected, as we do here. So it becomes now V equal Kcat times ET times S divided by Km, and the Kcat over Km is a very important factor for enzyme. It's a parameter that we call the specificity constant. We talk about that in class, and we gave a few examples saying that some of these examples shows that this enzyme are very good, and they have a good Kcat, but not very good and have a good Km. So the combination of both is what's making very good enzymes that has very high specificity, and also has a very good turnover number. So that's what we have been looking at these enzymes. We gave some examples just to highlight that, and I pick up the example of the enzyme that we isolated from these insects. That's called APOL-PDE. Which had a turnover number of 127. One might look at that and say, this is not very nice compared to acetylcholinesterase that gets 1,000. But it's compensated by the fact that this now has a good affinity here, substrate specificity here, altogether at 1 × 10⁸ molar minus 1 second minus 1. This is about almost the limit that one can have the substrate specificity for an enzyme. So it's compatible with acetylcholinesterase. It lost in KCAT, but gained in the specificity, which is much more important here. Acetylcholinesterase is dealing with a place where no other substrate is there. The only substrate is acetylcholine, basically. So acetylcholinesterase does not need to be that very specific. It's good to have high specificity, but it does not need to have as high specificity as a pheromone degrading enzyme, which gets hit by lots of compounds coming from the air, getting the antenna of the insect, and the insect doesn't want to spend time degrading these compounds that are not important for detection of where's the female, because ultimately what the male wants to do is to find a female and share the genes and get reproduction. So it's focused, and that's why these enzymes evolve that way. So it's a combination of both factors. A couple of things important about inhibition. We talk about the different types of inhibition. We talk about the competitive inhibition, the one that we discuss more in detail because it's one of the most important ones. Not that the other ones are not important. All of them are important, but these competitive inhibitors, we discussed in class that they change, the Kmax is, the Vmax still remain the same, just we have to have a little bit more of the substrate to reach that maximum. But the Km, the apparent Km changes, so that increases the Km, so gives the impression that the affinity decreases, but in fact, it's not the affinity that decreases, the apparent affinity, so that's why we call the KM-APP. Important things is to keep in mind that competitive inhibitors, they have a resemblance with the substrate. There's no way for a competitive inhibitor to bind to the bind pocket if they don't have any molecular fingerprint, sort of speaking, of the substrate. So if they don't look like the substrate, the enzyme is not going to be triggered by that. So a inhibitor, a competitive inhibitor, is always designed to be look like a substrate so that the enzyme gets occupied with these guys. And some of the enzymes are not going to be available to do the job for the substrate. Sometimes it goes a little bit in excess, like I showed the examples of sarin and some other of this material that they are using in war and warfare. So those are inhibitors that are a little bit more strong as they bind, they compete, but they damage the enzyme permanently, so the enzyme is not recoverable. Okay, some of them, like organophosphates and the mild ones, the enzyme can be still recovered. For example, if a person is intoxicated with some organophosphate insecticides by being exposed to those insecticides in a farm or somewhere else, it's possible to recover the patient by recover the enzyme and go back, life go back as normal. We also talk about using of those compounds, these inhibitors, in the case of disease like Alzheimer's disease, because it looks like the numbers of acetylcholine that's available is not enough. So it would be better to slow down this enzyme so that they don't degrade that very quickly. That's why they titrate a little bit the patient with some chemicals that's going to first make life better a little bit, because then we try to make a better balance of the existing amount of acetylcholine in the brain of the patient. But look at this graph. That's what's important for us. The disease and the other things are illustration. What's important in here is what we see in a graph like that. We see the 1 over the max and 1 over Km. And when we see an important feature of the competitive inhibitor is not only that they resemble the molecule, but also that the graph goes like that. The Lineweaver-Burke plots, we have a change in the Km. The apparent Km is increasing, and the Vmax remains the same. So that's competitive inhibitors increase the apparent Km, but Vmax remains unaffected. They resemble the substrate we already talked about. This is the example that we show in class, the example of Viagra, that it was one of these inhibitors that had been designed and it has made it was so successful as a product that it made billions of dollars and one of the big industries. There are other inhibitors like the same type that is existing, other names, but they are very similar and they all operate in the same mode. We talk also about the uncompetitive inhibitors that bind only to enzyme substrate complex. The enzyme binds to the substrate, then these guys come in and bind to the enzyme, make the enzyme useless for generate the product. All we want with the enzyme is not only to bind to the substrate, we want the enzyme to bind to the substrate and turn out that product. If the enzyme do half of the way, it's no good. So that's what these guys do. They interrupt the process midway. So that's the so-called uncompetitive inhibitor. The hallmark of these uncompetitive inhibitors are these parallel lines that we are going to see in the plot, because that's what's important for us, is to identify this plot and relate it to what type of activity is going on. So both the Vmax and the Km apparent, they both increase in the same, decrease in the same way. So therefore, what we see at the end is that they become parallel lines, okay? So that's what we have here. Km and Vmax are affecting parallel. Slope is constant because both decrease. So decrease the numerator, decrease the denominator, the ratio is become the same, right? So we talk about also the pure non-competitive, which the Vmax decrease, but the Km remains the same. So this is the pure non-competitive. It's interesting because we have three major examples that we have to keep in mind. One is that the lines is parallel to each other, right? So both things decrease. One, the Vmax does not change, and another one, the Km does not change, okay? So Vmax is going to decrease in here, but Km is going to remain the same. So it's a pure non-active, binds to the enzyme or enzyme substrate. So when the bind of AI does not affect the bind of S, the bind sites are distant, there's one situation that becomes like pure non-competitive. We talk in class also about the mixed non-competitive, two different types, but this is very low yield for this kind of level of class in here. So I would concentrate on these three types, like to look at the competitive one that we just talked about, the Vmax, no change, but the Km increase. That's the Viagra type in here that we're talking about. That's the organophosphate. There are the Russian agent chemical that we talk about in class. This is the uncompetitive, the decrease and decrease. Those are the parallel lines that we're talking about. And this is the pure non-competitive decrease Vmax, but Km becomes unchanged. So there's a point there in the line that we see, all this line comes and measure in the same point. In another word, saying that the Km remains unchanged. Last topic that we covered in class was this lipoproteins, that we make it very clear that these are not proteins in the sense that we study like the other units that we study like PBP or myoglobin or any other things, or carbohydrates for that matter, but rather they are a particle. They have a protein and lots of things together. And this structure normally carries a protein there. It's called the apoprotein. And there are different types of apoproteins. There are basically 5 types of lipoproteins that we have, the chylomicron and the other things. But I'm not going to talk about all of those, and we didn't cover all of those in class. What we discussed, it was LDL and HDL. We focus on these two because those are very important. Not the other ones are not important, but the other ones are more complex and it's more for a more advanced course in physiology or things like that. But let's focus just on these two for the sake of our understanding here. So this protein is going to be different. The ratio of protein to the other compounds that are here that makes this mix is going to be different. So they carry here in the center these triglycerides. Those are the energy. So this is carrying from one side to the other. It's delivering a fuel to the stations, okay? And they have also cholesterol, some cholesterol that are not esterified. They stay in the bilayer membrane, stick there, and some cholesterol that are esterified gets in the center. So remember, proteins are beautiful because they pick up this long chain and they fold and they make things very compact. So the more protein we have, the more compact these structures are going to be. So one difference between this LDL and the HDL that we talk about in class, it was the density, right? The lower density and the higher density. Lower density means what? Volume is larger for the same mass, right? So the density becomes small. So why the volume becomes larger? That's what we see here. We have a little amount of protein compared to these other things. In the HDL, there is more protein. So more proteins compact very well. So proteins make the density, the particle more dense. So the high density and the lower density differs in terms of the content of protein. These proteins that make this, the apoproteins that make this LDL and the HDL are also different. The LDL is part of the family. There are many other, three others major ones, like chylomicron, I mentioned, some others that they all have at least the ApoB100. HDL is the only one which does not have ApoB100. They have ApoA1 and the other apoproteins. But ApoA1 is very important for the structure formation. Without this protein, there will be no particle, right? Or how this, this fat and all these things will be in place with the lipid membrane bilayer on. They need the protein as part of the structure to become the lipoprotein. But also, these are ligands for receptors. These proteins, this HDL, one of the major, there are many functions, okay, to avoid inflammation of the walls and things like that, many other functions. But one of the functions is to carry out excess of cholesterol in the blood back to the liver and say, take it back, we don't need, that's too much. How the liver is going to recognize that there are too many things floating around there. But this HDL has this ApoA1, and that's a protein that's going to become the ligand for the receptors in the liver. So when they see it, they talk to each other. Okay, so that's how they deliver, because they carry that message through that receptor. ApoB100 cannot do the same thing because the receptors are not going to be recognized. What did we say about the LDL in class? One important issue is that LDL get oxidized by these free radicals, and they start being not recognized because APO also has a recognition for the tissue where they're going to deliver the material. So remember, these are particles carrying lots of triglyceride, cholesterol. Those are all important for the function of the body, and they have to bring and deliver those things. But if they deliver that and they recognize by the receptors, and then they are going to accept. There's a process. That's a beautiful process, by the way, but we didn't have time to discuss that in class. So how do they intake these particles inside of the cell? When they get oxidized, those receptors do not recognize anymore. So those LDL stay moving around. They are now oxidized form of LDL. What happens with time? They started to making accumulate, and it becomes inflammation process. It becomes the so-called foam cells, which cause atherosclerosis and many other things. So HDL is a good guy that goes around and pick up those excess of cholesterol that are sitting there and drop those cholesterol, bring back to the liver and the liver back so that they're going to be recycled. And if the liver doesn't need that because they already have enough, the body's going to be dumping that, and it maintains the homeostasis of the system. the good cholesterol, the bad cholesterol. That's the name that people give to this protein, although many people in the field hate this nomenclature because they are not good and bad. They are both good, but in different ways. One is very good to clean up the mess that sometimes is caused, but both of them are very good. Without LDL, there will be no energy to do all these activities that we do. And finally, we talk about one example of this aquaporin, and we talk about the discovery of Peter Agri made about these aquaporins, and finally we have the closing of the lectures with Peter Agri give us a message about the importance of this aquaporin in terms of transport of water from one side to the other. So that's all the material that I want to do, but maybe I could do here now is to do a little bit of some selected question from previous final exams. It's not going to be necessarily things that are going to be there on Wednesday, but just to give you an idea, because students always like to have an idea what kind of questions might we encounter. So let's give an example, and obviously it's not going to be the same question, but at least you see what's the way of thinking for that. So here's one example, and this cartoon here on the right, which has presented in class, depicts an alpha helix, traced dashed lines, like the ones that appears below, to highlight the hydrogen bonds are formed within this peptide chain. So let's do that here, shift gears, and so we're going to be looking at these peptides that we're going to be looking at where there's CO and the NH. So let's find it then here. There's one here. Okay, so I hope you are following there. That's another one that's forming here, so that I will have to trace it back. So basically, I'm asking students, show me what I show in class, right? So I get one other one here, that this one here has a pair also. Not all of them are going to have a pair, right? And there is one more. Yeah, this is 5 here. Perfect. So we have all that could be done. There are, in the C terms and the N terms, there are donors and acceptors that they are not going to have a pair. So it stays like that. So the other question is, what's the length of this structure, right? So we have here one turn, 3.6 residues, and 3.6 times 1.5 is going to give 5.4 angstroms. All right. And the last part is asking to write the names of two proteins, different proteins, proteins that are that are going to give here the name of pheromone binding protein. Still have a little bit. And the myoglobin. The question asking for different families, right? So we have to be careful not to give myoglobin and hemoglobin as two answers, okay? So one of the two is one part of the answer because they ask for different families. But we could have gave keratin here and it would be acceptable as well, because anything that's an alpha helix would be acceptable here. All right, so that would be the type of one question that we might encounter someday here or there. This is another one. Let's zoom up this one here so that we can read a little bit better. Okay, so let's try to, to zoom in here and to say, this question is asking the oxygen saturation, right, curve, and the different condition with the human hemoglobin at 37. Highlighted that thing. pH 7.4 is important also. And they give some numbers there that are not important, the good fitness, goodness of fit and things like that. And this comes from same temperature, that's important, temperature is not an issue here, and the three other factors. And now one curve is shift to the left and others shift to the right. So let's mark it there, shift to the left and shift to the right. And the question is that identify the factors that cause this thing and the show below. Okay, so let's trace before. the curve for the that we just discussed today. Oops, the hands are a bit shaking here now, but let's get this curve going. Okay, so for the right shift, we have pH, lower pH, that the Bohr effect, right? Lowering pH. We have also, if we increase the BPG, we also shift to the right, right? So let's put BPG increasing, CO2 increasing also, and T increasing. T increasing, right? So, and for the left, just to be the opposite of this thing here. Just keep in mind the acidity that could be one way. So we could pick up for those curves anything you want. One of these three, it has to be BPG, pH, and CO2 because you cannot use temperature that was the same. So let's use BPG for this one here. How can I make BPG for this one here if the curve is going to the left? So going to the left is because we have a decrease in BPG. That's right, this thing now, decrease in BPG or increase affinity for oxygen, right? Remember, if you lose the BPG, like expired blood, for example, expired blood lose a BPG, so increase affinity for oxygen, right? Affinity for oxygen increasing. For the other one, let's pick up either CO2 or pH, it doesn't matter. One for each, right? So we have to write down, let's pick up CO2 for these ones. CO2. So we have three of them and they change in the same way so that we have to pick up one for each. Okay, so CO2. And what happened to CO2? This is the maraschino one. This is the one that's going to the right. So it's going to the right. It's going to be increasing CO2 concentration, reduce oxygen affinity, right? Increasing in CO2 concentration, reduce oxygen affinity. Reduce oxygen affinity. And finally, pH. Finally, I have to use pH now for the third one. And if I use pH here, I use pH now, then what will happen? pH going to the right. That is exactly the Bohr effect, right? Decreasing pH is going to cause reduction in the affinity of oxygen. That's the Bohr effect. That's an easy one, right? And I'm going to tracing below all this Km so that we see what's happened if the Km is increasing and the affinity decreasing, right? So let's complete with this one here, increasing. You see there, the Km is increasing. So the Km is increasing from the left to the right. So the affinity is decreasing, right? So that would be the answer for this type of question. You see, I don't like it to ask things straight. I just like it to ask the thing, well, a little bit of a thinking there. So when you see my questions, always think a little bit, don't just jump in the question. I will tell you that from this exam, probably you are not going to need the full 2 hours. I will not think so. I can't guarantee that, but it's question that if we don't know or you don't know, there is not much in between, okay? So if you have a good command of the material, we're not going to need the full 2 hours for that exam. If you start to answer the questions and find out that, wow, I'm doing so well and I don't need more time, I'm doing something wrong here. No, it's because the exam is a straightforward exam, okay? Another question that's also worth 10 points. That this was a question that appeared before. And yes, examine the graph below. Let's put the graph here and calculate that. So examine the graph below and estimate Vmax and the Km. So we have this curve in here. We don't need to go back and get the line with bar plots for this thing. It's estimate. So give me a number very close. I'll take something. So I trace this thing in here and I consider this 0.07 as my maximum velocity. Okay. If you say 0.07 to 0.65, all of them are going to be taken. If you take 0.03, you are out. Okay. So anything that's close in here, that's good enough. That's just an idea. We're talking about estimation. Now, half of that is 0.035. So let's find here 0.35. Okay, oops. Then went down a little bit. Yeah, anyhow, something that's close to 1 there. If you say 1 micromolar, that's good enough. If you say 1.2 micromolar, if you say 0.9 micromolar, I'll take it. I will not take it if you say 3 micromolar or something like that nature, okay? So that would be the Km, approximately 1 micromolar. So Vmax, 0.7, Km, approximately 1 micromolar. That would be the answer for part I. Part II estimated the half-lifetime of this reaction. First of all, we need to know the rate constant because we know the half-lifetime, right? That's a formula for that. So let's take the K first, which is Vmax over Km. We already know that. We have Vmax in here. We have Km. 0.07 is the Vmax divided by the Km. In this case here is 1 micromolar. So we have micromolar. The unit at the end is going to be second minus 1, and 0.07 here because you don't need a calculator for that one, I guess. So 0.07 second minus 1. So now that I know that, I have t and a half. It's going to be 0.693 divided by k, and k I already calculate, so there's 0.0693 divided by 0.07, and that's going to give us, that will probably need a calculator, but it's very simple, and it would give us 9.9 seconds. The unit of time here is second because the unit of k is second inverse of second to minus 1. 9.9 seconds. That will be the answer for this very simple question about enzyme kinetics, okay? So that would be, let me clear up this thing here and put this final answer for that particular question. Not going to do a very exhaustive thing here. I still wanted to answer a couple of questions that come from the chat. So I ask people to hold the question to the end. Let's do another one. Let's do one more here. Enzyme inactivation, degradation of an insect pheromone was studied with a putative pheromone degrading enzyme. So let's look at that in closer view here and highlight what's important. This study of the pheromone degrading enzyme, the Km was given as 3, 10 to the power of -4, and it started with a concentration of 1 micromolar. It was observed that after 1 minute, 5% of the substrate has been consumed. That's to say 95% of pheromone was still intact after 1 minute. It was not used. Calculate the rate constant for this reaction, the percent of substrate, and some other things. So let's see how we do that. Okay, so it's S equals S0 times E over KT. We know that 95% of the substrate was still remain, so 0.95 of S0 equals S0 times E minus K times 1. Why I want to do that? Because regardless of how much is S0, I'm going to cancel this thing out here, and I'm going to end up with an equation that's 0.95 E equals to negative power of K. So we can solve that and find out how much K is. We take the logarithm, the natural logarithm of both sides. And then we know that log of minus EK is called minus K log of E, which is log of E base E is 1, so it's minus K. So therefore K equals minus the logarithm of 0, not beta, but K. K equals minus logarithm of 0.95, which is equal negative from the formula, and we calculate 0.95, that's 0.051. The logarithm itself is negative, it's minus 0.051, smaller than 1, right? So that's why negative. So K equals 0.051, and this is in minutes because we're talking about minutes here, minutes and minus 1. So now we have the K now. Calculate the rate constant. We did. The percent of substrate after 5 minutes. Let's say 5 minutes now. Let's use the time now is 5 minutes. T equals 5 minutes now. So let's apply the formula. S equals S0, E to the power of 0.051 times 5. So that's this calculation here that we're going to need that. So that says equals S0 times 0.775. That's what it needed. All this number here, all this calculation is 0.0775. Okay. Come on, baby. Times. Okay, 0.075. 775, finally going. So therefore here we can say that this was S was 7.5%, right? 7 at that point was 7.75%. So how much was used? If you have still left over 7.7%, it's because you use only 22.5%. The delta S, the amount used, was 22.5%. Okay, 22.5%. All right, so what they want more? They wanted the Vmax and the time that it would take to consume 50%. All right, so let's do that. We can do Vmax very easily because we know that the K equals Vmax divided by Km. So let's do that. K equals Vmax divided by Km. Keep it going here. The signal is not going. Let's see. Come on, babe. This thing is not as fast as I want, but I don't want to take too much of your time. I know that you guys have a precious time, and I don't want it to be wasting your precious time, but sometimes things doesn't go. All right, so that's equals, K equals, all right, Vmax over Km, right? Vmax over Km. Therefore, Vmax is going to be equals K times Km. K we have, Km we have, so let's plug in these numbers. 0.051 times 3 times 10 to the power of -4 molar, and the other one was second to -1. So let's put the Vmax in here now. It's going to be equal so this is going to give you 1.53 10 to the power of -5. And this is going to be molar per minute. Molar per minute, -5. Molar per minute. Since it's 10 to -5, let's make 10 -6. This is useful here. Equals 15.3. 50.10 to -6. 50.3 10 to -6 molar per minute. I just want to make a better unit there, right? So that's equal 15.3 micromolar per minute. Micromolar per minute. That would be the Vmax, okay? Calculated Vmax now, half time now, 0.693 divided by K. K we already have is 0.051. So gives 13.6 approximately. 13.6, and this time is going to be in minutes because we are talking about constant units here that carries minute. 13.6 minutes. All right. Okay, so that's the summary here. We have all this problem worked out. That's a problem that will take a little bit more of time than some of the other problems that we did before. A little bit more calculation, but that's not a big deal. And this was worth 10 points anyway, 10% of the test at that particular time. Maybe you can do one more before I entertain some of the questions. Let's do this one here. The odorant binding protein. This one here actually I did in the office hours for some of the students that attend my office hours, but let's do that here so that one have the same opportunity. This is equal opportunity class anyway. So the odorant binding protein is from CQ from the Southhausen mosquito, a possible vet of the Zika virus. It's additional information, doesn't matter, right? So this problem here says that this is a helix. You see that cysteine is there, 26, right? All the cysteine is there that we mark. Of the 6 alpha helix, alpha 3 spans from ASP 48 to 1 to 62. And the C-terminus alpha 5 is lysine 93. Those are all relevant information to help you solve the problem, okay? Then asks, first of all, what's the length of alpha 6? What's the length of alpha 6? That's the first question. So let's find out. Alpha 6. Do you see alpha 6 there in your screen? Alpha 6 in your screen there. Marking here, alpha 6, okay? Alpha 6 is starting from 102 to 118. That's what the problem told you. You don't need to know that. It's marked in here, and it tells you that also the information in the problem. So how many residues are there? If you started from 102 and 118. So it's going to be 118 minus 102. That's 16 plus 1, right? 16 plus 1. But to be honest, I would take it either way. If you don't do this 16 plus 1, because if you have 1 to 3 and then you subtract, you have to add 1, right? But if not, even so, I would take that because the right way would be 16 plus 1 would be 17 residues there. But if you take only 16, I'll take that the answer is completely fine. So that would be 16 times 1.5 because of alpha helix. That would give us 24 angstrom. If you read entirely the right way, it would be 17 times 1.5. In that case, would be 25.5 angstrom. 25.5 angstrom. Okay, so that would be the length of this alpha helix in here, 24 or 25.5. I'll take any of these two answers. That's okay. Next, I ask you to clearly label the 4 cysteine residues in red. So let's follow this cysteines here, okay? So we have the N terms of the protein. We have the alpha helix sitting there. Let's look at that very closely here. We have the alpha 1 helix, right? So let's follow that alpha 1 helix. Okay, so let's see here, alpha 1 helix. And that would be the cysteine 26, the first one there, because that's the first one that we have in the group, right? So the first one that appears in that alpha helix. Now, if you follow that alpha helix, we have the cysteine, follow that alpha helix, we go that alpha 2, right? And then comes to the alpha 3. So now we know that alpha 3 is coming from the left side to right side, right? The alpha helix is coming like that for the N to C, right? So therefore, these two cysteines that are there, we know that they're going to be the cysteine, one of them is going to be cysteine 53, another one is going to be 57, because the order that they come, okay? 53 and the 57. Then we keep going here, and if you go next to the alpha 6, for example, if you look at the alpha 6, that's a cysteine right there in the alpha 6, and the alpha 6 is starting with 102. That cysteine has to be 104, right? Because there's 102, and it's lost in the beginning of the alpha helix. That's a cysteine there that has to be then 104. Okay, so I mark here 104. Maybe a little bit too crowded there. If you are uncertain that we're going to see that, maybe you can pull it out, put it in a nicer place. So that's very clear cut there, 104. And then we keep it going, and there's another cysteine in the same helix, and the helix ends 113. So there's a cysteine that's 113. Cysteine ends with 118, and we have 113. So this one has to be 113. Okay, 113. And the other one, you see the alpha 5 now there? the hint there in the problem say that alpha 5 and the C-terminus is lysine 93. So if at the end of that helix is lysine 93, the next one has to be lysine 95. That's very close to the end of that. So this would be cysteine 9, 5. There's a little bit of thinking in here for this problem. It's not a straightforward, how long is the length of this? No, it's a problem that it requires a little bit of thinking, okay? It's only part of that problem. So, and the question now is that what kind of post-translational modification would happen? Disulfide bridge, right? Disulfide links. And with an arrow, show the C terms of the protein. Let's follow the C terms of the protein here. That's alpha 6 is ending there. Let's follow alpha 6 now. And that's, we see the end of the protein. Let's mark it there with a very clear cut with an arrow so that when we grade, we don't have any missing understanding. There are lots of questions normally in those exams that come with structures of proteins. Structures of proteins, we have to look at the structure and decipher what dissect the information that it is required. Okay, so it's getting a little bit late in here, but I'm still going to do a little bit of questions. So now I'm going to need this the help from Kai to bring in the questions. Okay, so I know that you guys have been chatting there and exchanging information with each other. Probably have some of the information, but now let's move it to the chat room with a special thanks to Kai Ming Tan. Like I said, he was one of the students that took this class before and nicely volunteered today. My son has been helping before, but today he's busy on the night shift, so I have the help from Kai Ming Tan. So let me stop sharing here. And go back to the, all right, so shall I start with this one? So this one here started and it goes on with this one, okay? So lots of ones. I'm going to try to be quick if I see that there's a, okay, so that one I can't answer, KM or KD, so correct, I don't know which context was that, so I'm going to skip that one. Okay, so that's a conversation between the two of them and the, so that's hard to say. Carbamate is HbNH_COO. Carbon amino hemoglobin is HbNH2. Yeah, that's I don't see the question. That's yeah. So Kai, let's concentrate on the specific question because this is a dialogue between students, and that's perfectly fine. But nothing for me to go and answer specifically. It would be more with competitive inhibitors, the K maps increase, but the mass remains unchanged because one of the substrate binds to the enzyme that catalyzes the reaction. I think that's another part of the conversation that Jess is responding to other students. And so why don't you ask a specific question that you have for me now, because those are part of the conversation between different people. Okay, so let's see here. What is S to minus 1, if that's at the top of the numerator? Or S minus 1 is that the inverse of S. So S to the power of negative 1. Okay, so the other time the questions were a little bit more clear. That's not a part of the conversation, so it's hard for me to get those questions and answer all your. All right, so there's a problem concentrating mother said. Sorry for me mumbling around in here, but I needed to go over this thing very quickly. This is live TV, so we don't have time to do much. Yeah, that's a good, I think Jesse also to everyone, 8:30 p.m. I think this is about the the difference of amino acid residue, right? If you have something that has 2 units, right? And then we say 2, and we start with 1 and end with 2, okay? So if you subtract that 2 minus 1, we're going to get 1, and it's not 1, it's 2, right? So you always have to add the 1, all right? So if you have amino acid from 1 to 15, then we say 15 minus 1, 14 plus 1. Okay, so you have to add that to 1, and the Jess is right about that. So let's see if that's a specific question here. Uh, what kind of problems should we expect if the older material? I think Niha was asking this question. Well, that could be anything, right? What causes the conformation changing in bone mixing motor PBP? That's a good one. And Marisa is asking this question. That's pH, right? Lower pH. And that's what triggered the conformation now changing in the ferrobond binding protein. We talk about the glycerol. What is it important? Yes, glycerol is important. Glycerol is that makes the triglyceride, right? Glycerol is an alcohol with three alcohol groups there, and the fatty acids are acid, right? So they react with each other, they form the ester, right? So the triglycerides that they carry the energy for the body is in the form of a glycerol bound to three fat acids. One more coming here, fresh from the press. Could you explain the Russian spike competitive inhibitor example? Yes, I could always explain something about Russia. Anyhow, what I was trying to say about those agents there, they are competitive inhibitor. The same thing like they are organophosphate, a carbamate insecticide is a competitive inhibitor of acetylcholinesterase. What's happened with the siren agents and with some of these warfare type of chemicals, that they were made stronger than these other inhibitors. So they don't inhibit only, but when they bind to the active side, remember that I talk about the serine and the active side of acetylcholinesterase. When they bind to the serine, they become covalently bound to that serine in a way that's impossible to break that covalent bond. All those chemicals, including acetylcholine, they bind to this acetylcholinesterase covalently, but the weak bond, so that the water molecule comes in and break this the bond between serine and the leftover of acetylcholine, for example. However, in the case of these agents, they are so strong that when they bind there, this water is not going to take out this and recover this enzyme. When the person is intoxicated with organophosphate, the doctor in the emergency room would administer a little bit of PAN, which is a reagent that does exactly that. Clear up those sites in the enzyme. But if it's an agent like those, that's very difficult because they are not easy to remove. So basically, each enzyme that got a molecule of those agents is basically lost. And if you have enough enzyme that we still can keep going, that's fine. But if you don't have enough enzyme, the level of intoxication was very high. So that's the end of it, right? So this is the weapon of mass destruction. This sarin gas has been used. Even recently, we hear news about it, people using in Syria against their own people, right? So those are terrible and painful and terrible that they cause. So that's why they are so cruel that people tended to agree already that they're not being used in warfare anymore. But we see exception here and there against the law, but anyhow, that's what happened. So that's what your question. And what was the question? Is the release of hydrogen buffer that occurs in the blood cell proposed to release O2 from the HP? Release of protons is associated with that, but it's release of protons so that it keeps going from one side to the other, right? So that's kind of a transport also, right? Do all drugs act like competitive inhibitors? No, there are all the different types of inhibitors. I just gave a little bit more emphasis to one of them. That's the competitive inhibitor, because I talk about the organophosphate, I talk about Viagra, I talk about this and that with that particular one, but there are all different types of inhibitors, okay? So the drug, the pharmaceutical industry heavily targeted this thing as a target for development of new drugs. Like the same thing we do with this Genentech producing this antibody and things, that's another target, but that's a huge amount of research that's been doing in enzyme inhibition to generate products that can be utilized as medicine. Uh, how did he use the lysine to place the cysteine? Oh, in the last problem, what I did, it was the problem gave a hint to you because it's very crowded there. You could get confused. So I gave an information that say, hey, this lysine 93 is at the end of the alpha helix 5. So, and then you see soon after that, you see a cysteine. If you see the lysine before was 93, amino acid very close to that has to be the 93. So I was trying to be nice to give a hint so that we don't get confused, okay? Can you explain the C terminus arrow in the last question again? I don't get why alpha has was before alpha 6. No, alpha 6 was not before 5. Just I approach the problem and look at the alpha 6 first. But if you follow the tracer there, it's not before. It's alpha 1, 2, 3, 4, 5, 6. That's always the case. That's by order. Except that the rotation that is in here, there is no rotation that we can put all these things very clearly to you. So in order to make it clear, we give some additional information like the one that I just mentioned, okay? Should we still go over thermodynamic equation like the G equations? I hate to say what you should do or should not do, but I would say that's low yield at this point for the final exam. Professor, just to clarify, have a large specificity constant means the enzyme is better. This occurs a large, yeah, it's hard to say. Okay, so specificity constant encompasses both KCAT and the affinity, right? So when they have a very large one, that's a good thing. If they have a combination of both, a larger turnover number and a higher affinity, this is better. But it's a combination of both. That's exactly when we look at the enzyme. We don't want an enzyme that has a substrate specificity very low. We want that enzyme to be as good as possible with a combination of a KCAT and KM. Okay, so that's what's important about the enzyme. What's the importance of protein folding? Oh, it's very important. Remember, I didn't have time to go today about every single aspect that we covered in the lecture. This was supposed to be a 30 minutes, 45 minutes. Oh, my goodness, it's already 8 something. Even so, there will be no time to go over every specific points that we have in the lecture. That's why we have the lectures. Here is just an overview to, help you guide a little bit so that we can go and continue your studies. Don't take this thing as a final for everything, right? What's the function of myoglobin in the blood? The major function of myoglobin in the body is storage of oxygen in the periphery, in the muscles, okay? Storage of protein. Remember that you talked in class about going to buy meeting and we like this meeting when it's reddish. It's because that's meeting that is still full of oxygen, right? So it's fresh. So that oxygen is oxygen bound to myoglobin, not hemoglobin. Hemoglobin was in the blood. The blood is not there, basically. For the last question you did just now, where should we start when you follow the direction of the alpha helix? That's a very important question. Alpha helix always started from the N to the C terminal, right? So we have to find out where is the N part of that so that we can follow. Remember, when I started the question there, for example, alpha 3 is displayed there, but we don't know alpha 3 is coming to top to bottom or the bottom to the top. So how did I do that? I went to alpha 1, alpha 2, and I follow, and I see that's coming from top down. That's what was important. If you don't do that, you get confused, and probably you get these two cysteine residues in the reverse order. All right, so that's an important question. Now, let me rephrase again. So what I did was I know where alpha 1 is, so I follow alpha 1 and it went to alpha 2. How did I go to alpha 1 and alpha 2? Because I know that they go from N to C, right? So I went to alpha 1, alpha 2, and I follow down and I come to alpha 3. Then I know that I reach alpha 3 through its N terms, not to the C term. And then I went all the way down and ends with the C term. Okay, that's very important question. Does myoglobin and hemoglobin have a chance change like a PPG? Is it negatively? Does myoglobin and hemoglobin have a change like PPG? It's negatively charged. I didn't understand this question, but myoglobin has nothing to do with BPG, if that's your question. Okay, BPG binds to hemoglobin. Remember, we needed to have this quaternary structure and this is space formed by these various units to have the space for for BPG. Myoglobin is a single molecule, right? There is no place there for BPG to bind. So BPG's bind is a cavity formed by different units. Remember? So BPG and the hemoglobin goes mano a mano, but the myoglobin is out of the picture when we talk about the BPG. I think that's all. We have answered all the questions that came from the chat room. I say 8:20. I'm kind of run out of triglycerides now delivered to the teachers. I needed to get some food. One more question is coming. And it's going to be the last one, is on the way from the chat room here. And again, I appreciate you so very much for Kai. Kai is also studying for his final exam, so he's on another level now. He already graduated, but I appreciate he doing that just come here. Just to clarify, we can actually see the cysteine on the last problem in the visual. We just need to ID where they should be located on each helix. Exactly, the cysteine was denoted by red dots. The red big balls there would say, these are the cysteine. You see on the top of the figure, it says denotes cysteine, a big dot. You are perfectly correct. There was no cysteine per se there. We do not see the chain with the SCH there that would be identified. This could be another type of problem. There could be problems that could have amino acid residues there, and they ask you to identify those amino acid residues. Okay, so it's 8:25-ish now. I think we needed to end here. Kai coming here, and thanks so very much. That was very, very helpful. Without Kai, we could not do that. It's always good to have people volunteer coming back to this class. I appreciate that very much. Thank you all. Take a good rest and resume your studies. Don't take this for all the studies I'm going to do for this 1 or 2. And I look forward to see you on Wednesday. And I wish you the best for this final exam. Thank you. Good night.
Good luck on the finals.
Thank you. That was great. Appreciate that. Without you, it would not be possible.